So, homework wise. Homework number 1 on chapters 1 and 2 is due tonight. On Pearson's Biolab and Mastering. And homework number 2 on chapters 2 and 3 is due on the 17th. In a week. We do have a lab today. I'll try and keep it short. Your labs from last week are up here. You can get them. They're graded. Generally, people did pretty well. Yeah. So we've been talking about vectors. The components of a vector are, we can break vectors down into their components. The amount in the x direction and the amount in the y direction. So for a vector, ax will be oh man, what's wrong? Ax, the x component will be the magnitude times the cosine of the angle, and the y component will be the magnitude times the sine of the angle. Trigonometry, quick review of trigonometry. Opposite over hypotenuse is sine. Adjacent over hypotenuse is cosine. Opposite over adjacent is tangent. Combining that with the idea about components and the Pythagorean theorem is that x squared plus y squared will equal r squared. We get that ax is a cosine theta, a y is a sine theta, and then if you want theta, tangent of theta is a y over a x, and a is going to be the square root of ax squared plus a y squared. So you go from length and direction to x and y components. Use these equations. Ax is a cosine theta, a y is a sine theta, where a is just your vector. And to convert from x and y components to length and direction, you use inverse tangent of ay over ax is theta, and a is square root of a x squared plus a y squared. You just came in, your name? No. Trey, I think I missed you when I was taking attendance. Yeah. So let's look at the signs of the components of vectors. If x and y are positive, it's in the upper, this first quadrant here. If x is negative and y is positive, it's the second quadrant here. If x and y are both negative, it's the third quadrant down here. And lastly, if y is negative and x is positive, it's the fourth quadrant there. When you add and subtract vectors, if you do so graphically, Nick, you just connect them head to tail, and the sum points from the tail of the first to the head of the last. When you add vectors using components, you find the components of each vector to be added. You add the components up. The x and y components separately. This is gives you the resultant vector. So you can connect them head to tail, or you can add the components. When you subtract vectors, you either add the negative of the vector, which is the same vector but pointing in the opposite direction, or you subtract components. So that was a sort of review of some of the stuff from Monday. Any questions about any of that? Okay. So let's talk about relative motion. So sometimes when you have multiple things moving or something moving on something else, their motion combines. This is what we're going to be using, what is known as Galilean relativity, where their motions combine in the simplest way possible, as opposed to what you would do for, say, special relativity or general relativity. So here you have a train traveling at name. Your name? Oh. Yeah. So here we have a train traveling at 15 meters per second, and a guy walking on the train at 1.2 meters per second relative to the train. So in both cases, and he could be either walking in the same direction as the train or in the opposite direction of the train. And if you want to figure out how fast he's moving with respect to the ground, his motion with respect to the ground, you have to combine the motion of the train and the guy walking on the train. So here, effectively, they add because they're in the same direction. So this will be, so the velocity of the person with respect to the ground is the velocity of the person with respect to the train, plus the velocity of the train with respect to the ground. This is the way I like to write it. So you can sort of see the pattern where the feet connect together. And let me. So in this case, this will be the velocity of the person with respect to the ground is going to be 1.2 meters per second plus 15 meters per second. So it will be 16.2 meters per second. And here, effectively the 1.2 meters per second is negative. So the velocity of the person with respect to the ground is negative 1.2 meters per second plus 15 meters per second. So it will be 13.8 meters per second. Because here they're moving in the same direction, they're going to add up. You're going to be going faster. Here they're moving in opposite directions, so they're going to cancel out some. They'll effectively be going slow. So the general formula, if you have some things moving, is the velocity of the passenger with respect to the ground is the velocity of the passenger with respect to the train, plus the velocity of the train with respect to the ground. So, velocity of A with respect to C is velocity of A with respect to B plus velocity of B with respect to C. So I'm using first letter is what's moving, second letter is from the point of view of. It also works in 2 dimensions. So if the guy is climbing a ladder as the train moves forwards, you would combine them as vectors. The velocity of the train with respect to the ground is this. The velocity of the passenger with respect to the train is this. When you add them together, the velocity of the passenger with respect to the ground will be upwards at a slight angle. So if you have a worker climbing a ladder on a train, that he's climbing with a speed of 0.2 meters per second up, and the train is traveling at 0.688 meters per second to the right, what is the speed and direction of the motion of the worker with relation to the ground? So you know 2.4 meters per second up is the velocity of the person with respect to the train. And 0.68 meters per second to the right is the velocity of the train with respect to the ground. So you can combine those to find the velocity of the worker with respect to the ground. So I'll give you a couple of minutes to work on. So here, well, I gotta erase these. We know the velocity of the person with respect to the train is 0.24 meters per second up. So it's 0.24 meters per second in the y direction, positive in the y direction. and the train is traveling at 0.68 meters per second to the right, the velocity of the train with respect to the ground is 0.68 meters per second in the x direction. And if we combine these, we want to find the velocity of the person with respect to the ground. Specifically, we want to find its speed and angle. So let's find the velocity of the person with respect to the ground. Velocity of the person with respect to the ground and is equal to velocity of the person with respect to the train plus velocity of the train with respect to the ground. So the velocity of the person with respect to the ground is 0.24 meters per second in the y direction, plus 0.68 meters per second in the x direction. Rearranging that to be in standard form. The animations got messed up. Let me just quickly fix these. And get back to where we were. Sorry, rearranging that to be in standard form. VPG is 0.68 x hat plus 0.24 y hat, all times meters per second. But we want to find, this question is asking for the speed and direction of motion with relation to the ground. So we know what this vector is, but we know it in component form. We know the x component and the y component. So we want to find the magnitude and the angle. So the magnitude of this is going to be vx squared plus vy squared, square root. So square root of 0.68 meters per second squared plus 0.24 meters per second squared, all square rooted. And that comes out to 0.72 meters per second. And then the angle is going to be the inverse tangent of Vy over Vx. X is positive, so we don't have to worry about anything beyond that. So 0.24 meters per second divided by 0.68 meters per second gives us an angle of 19 degrees. So from the point of view of the ground, it'll be traveling at 0.72 meters per second at an angle of 19 degrees. Question?
Yeah, why did you switch 0.24 y hat plus 0.68 x hat? Why did you switch that?
Oh, because we normally write x first.
Because it's x plus y.
Yeah.
Okay.
That's just because this is the standard form is x plus y.
Okay.
It's just conventional to put x before y. These aren't any different from each other as values, but usually you write x then y just for clarity. And it helps you, and if you do that switch in standard form, if you keep things in standard form, it's easier for you to see which part is the x part and which part's the y part. Which is why I switched them. Because this is VPT and this is VTG. And then I put the x first. Just because that's the normal way that these things get written. Okay, so a little more complicated problem. We have a boat crossing a river that flows at 1.5 meters per second. The boat travels at a speed of 6 meters per second relative to the water. And so the question is, what angle does the boat have to go at to go straight across the river, perpendicular to the shore? So sort of a quick doodle here. You have the velocity of the boat with respect to the water. This is 6. meters per second at some angle theta. Let me actually switch the angle around. So let's say that, okay, so we have a river. It is traveling at 1.5 meters per second. This is the velocity of the water with respect to the shore. Then we have a boat. The velocity of the boat with respect to the water is 6 meters per second. And I drew this wrong. Velocity of water with respect to the shore. The velocity of the boat with respect to the water is 6 meters per second at some angle theta. And they will combine to create something horizontal, which is the velocity of the boat with respect to the shore. So that's sort of the triangle you can draw. The river is going south, so to counteract it, the boat has to go a bit north. And we want to end up perpendicular to the shores. So the velocity of the boat with respect to the shore will only have an x component. The velocity of the water with respect to the shore has a y component. And we want to figure out what this angle is. That's sort of the approach. And so I'll give you a few minutes to work on that. So I'm just going to put this and pause this and see what I do. Oh. Okay. You actually put a drawing on the slide, but a little bit. So for this, the velocity of the water with respect to the shore is 1.5 meters per second. That should not have an error. The velocity of the boat with respect to the water is 6 meters per second. We want to find the angle of the boat with respect to the water. We don't know what the velocity of the boat with respect to the shore is, but we do know that it is something only in the x direction. So I drew a picture here. With the velocity of the water with respect to the shore, the velocity of the boat with respect to the water, and the velocity of the boat with respect to the shore. And I could have done this picture could have been a little better, but I think the one on the board is a little less confusing. Just because of the order, they both work. They're functionally identical. The one I drew here, I add water VWS before. This is VWS plus VBW, while this is VBW plus VWS, which is, the same thing. But, the one on the board is for the water flowing south. This is for the water flowing north. Doesn't actually make that big of a difference. And it's the same thing. The difference is just this is a little more intuitive in the order. It's because the W's match up. So it's a little easier to think of that way. But the math doesn't really change. This matches what's in the book a little closer also, but again, it's just which direction the water's flowing. Yeah. So the velocity of the water with respect to the shore. So the easiest way to figure this out is instead of trying to use this equation and find stuff, it's just, this is a right triangle. So it's a right triangle. We know this angle that we're interested in is the angle in the corner. So velocity VWS over VPW is the sine of the angle. And I wrote that wrong. That's a typo. Jeez. That I missed when I was scanning through this. So I get for copying things from previous slides. It's the sine of the angle because it's opposite over adjacent. So this, it's extracted best from the picture. We have the angle, we have velocity of the water with respect to the shore, opposite over hypotenuse, velocity of the boat with respect to the water. So it's opposite over hypotenuse. That is the sine. The VWS is VBW sine VW. So theta BW is sine inverse of VWS over VBW. You can also think about it as this is the y component. We're effectively using this equation here. The y component of VBW has to equal VWS from the picture. The angle is going to be the inverse sine of VWS over VBW. So the inverse sine of 1.5 meters per second over 6.0 meters per second, which is about 14.5 degrees. So these sort of problems, the best way to attack them is generally to draw a picture. And once you've drawn a picture, you can usually figure out where the numbers fit in, and you're going to end up with a triangle that you have to do some trig on. Any questions? So that's the end of chapter 3. So a summary. A scalar is a number with units with no direction. A vector is a quantity that has a magnitude, a size, which can have units, and a direction. The components of a vector, if you have some vector A, its x component is its magnitude, A, times the cosine of the angle, direct And its y component would be the magnitude times the sine of the angle. I'm not sure why the book decided to do A and B for these two. But that is from the book. In fact, I think I'll change the, if I can. Yeah, let's change these to A, because that makes more sense. I'll update the slides after this. Magnitude is the square root of ax squared plus ay squared. Direction is inverse tangent of ay over ax. If ax is negative, you'll have to add 180 degrees or subtract 180 degrees. Go to the other side of the circle. Yes, question? Oh, okay. To add vectors graphically, press the tail of the second at the head of the first, and the sum points from the tail of the first to the head of the second, the last. To add vectors with components, you add the components of the individual vectors, and then you can find the magnitude and direction. This is what you're going to do most often, because this actually gets you numbers. Unit vectors are dimensionless and of unit length. They indicate direction. The most commonly used ones are going to be x hat and y hat, indicating the x direction and the y direction. The position vector points from the origin to a location. The displacement vector points from the original position to the final position, because it's final position minus original position. Velocity vector points in the direction of motion. The acceleration vector points in the direction of change of motion. And for relative motion, v of 1 with respect to 3 is v of 1 with respect to 2 plus v of 2 with respect to 3. That's the general formula for relative motion. So that's chapter 3, and we're going to start on chapter 4. So now that we know about vectors and dealing with two-dimensional things, we can start on two-dimensional kinematics. Two-dimensional kinematics. So back in chapter 2, what we were doing was one-dimensional kinematics. So describing motion in one dimension. Now we're going to add a second dimension. So we'll be able to do two-dimensional kinematics. But we'll have to quickly stop sharing and reshare. So for two-dimensional kinematics, it's much like one-dimensional kinematics, except you basically add a second set of equations, a second copy of the same set of equations we were using for the other direction. So we'll be talking about things like projectile motion. So these are, various projectiles, paths that things can take. We'll discuss the nature of motion in two dimensions. We'll go over the basic equations of projectile motion. This is going to be the most common form of two-dimensional kinematics we deal with. We'll start with the general case, and then we'll look at the common, more special case. We'll look at the case with zero launch angle, with a general launch angle, and we'll go over some key characteristics and patterns in projectile motion that will generally appear because of its properties. So in two dimensions, if velocity is constant, motion will be along a straight line. So if you have constant velocity, motion will just be along a straight line. you'll have a constant velocity in the x direction and a constant velocity in the y direction. So your velocity in the x direction will be, if you're at some angle and you're traveling at some velocity v naught, your velocity in the x direction will be v naught times cosine theta. Your velocity in the y direction will be v naught times sine theta. And your position in the x direction, if you were starting at the origin, would be v naught x times t, and y would be v naught y times t. So just the sort of general structure you're dealing with is v naught x is going to be v naught times cosine theta, v naught y will be v naught times sine theta, and x will be x naught plus v naught x times t, and y will be y naught plus v naught y times t for constant velocity. So, if you have an eagle perched on a tree limb that's 19.5 meters above the ground, above the water, and it spots a fish swimming near the surface, it pushes off the branch and descends towards the water. The eagle maintains by adjusting its body in flight, it maintains a constant speed of 3.1 meters per second at an angle of 20 degrees below the horizontal. So you can say v naught y is negative v naught sine theta, or you can treat this angle as negative 20 degrees. Either one will work. So how far has the eagle traveled? Sorry, how much time does it take for the eagle to reach the water? And how far has the eagle traveled in the horizontal direction when it reaches the water? So what is the time it takes for the eagle to reach the water here? And how far is it from the shore when it does? How far has it traveled horizontally? So this is looking for time and delta x, displacement in the x direction. But yeah. So the approach to this problem, we need to break. So the general approach to two-dimensional problems is you break them in to an X part and a Y part. You break them into their components. And then the way you connect between components is time. So first, we're going to figure out how much time it takes for the eagle to reach the water. To do that, we're going to figure out its velocity downwards and figure out how much time it takes to reach the water. So what do we know? We know our initial velocity. We know our initial velocity's angle. 20 degrees down, the angle in that picture. We know the height that we're going to travel, 19.5 meters. We know we want to find the final. We don't know the final velocity. We don't know the X direction velocity, the Y direction velocity. And for part A, what we're looking for is time. And for part B, what we're looking for is delta X, displacement in the X direction. So for part A, to find time, well, equations-wise, we're going to use Vx equals V naught cosine theta and Vy equals V naught sine theta, because we're dealing with constant velocity here. I should put some more zeros in there. So the velocity in the X direction is going to be 2.91 meters per second. The velocity in the Y direction is 1.06 meters per second. But it's down in this case. The velocity in the Y direction is going to be the distance covered over the time, so the height over the time. So the time is the height divided by the velocity in the Y direction. So 19.5 meters over 1.06 meters per second gives us a time of 18.4 seconds. And the velocity in the X direction is going to be the change in X over time. Change in X will equal velocity in the X direction times time. So 2.91 meters per second times 18.4 seconds is 53.5 meters. And so I was a little sloppy with the directions and the signs in this. We want to go through and change those to make it a little clearer. Or do you want me to just go on? I'll do a quick change though, so you can see by making it make it a little clearer. It's just some minus signs. Minus. This is minus. This is minus. This is minus. These should have. Oops. 0, 0, 0, 0. This would get a minus and a minus, because we're going H down. So this would be minus over minus, and we get the same answer. And then this is basically the same. Just to indicate that it's moving downwards. The Y is negative, but also this is delta Y, which is negative H. Now, in general, motion in the x and y directions gets solved separately, and you connect them via time. So, not x plus x t dx squared plus equals v naught x squared plus 2 ax delta x, and then same thing for y. Y equals y naught plus v naught y t plus 1/2 acceleration y t squared. Dy equals v naught y plus acceleration y t dy squared equals v naught y squared plus 2 acceleration y delta of y. Those are the general equations you're going to deal with. It's just one set of the kinematic equations for x, and then the whole thing repeated, but with y instead. So the x and y directions should be solved separately. If you know time, you just use these directly. But often what you'll do is you'll solve one direction to figure out time and plug it in for the other direction. So like in that previous problem, we found y. We knew things about y. So we solved y for time, found time, then took that and plugged it in to solve for x. So as an example problem here, we have a helicopter that's in level flight with a constant horizontal speed of 11 meters per second. At time t equals 0, it begins to accelerate vertically at 0.96 meters per second squared. So this is v naught x. This is acceleration in the y direction. Assuming the helicopter's acceleration remains constant for the time interval of interest, and the horizontal, so find the horizontal and vertical distances, which it moves through in 5.3 seconds, and its x and y velocity components at t equals 5.3 seconds. So this is v naught x, v naught y is 0, acceleration x is 0, and x naught and is 0, and y naught is 0. For sort of the things we know. Starting at the origin, we're interested in the distance through which it moves, so that starting x naught and y naught are going to be 0, and so it has an initial velocity in the x direction, 0 initial velocity in the y direction, 0 acceleration in the x direction, but it does have acceleration in the y direction. So I'll give you a few minutes to work on this.
So, getting rid of the picture so we have a little more room to work. Our initial velocity in the x direction is 11 meters per second. Our initial acceleration in the x direction is 0 meters per second squared. Our initial velocity in the y direction is 0 meters per second. Our acceleration in the y direction is 0.96 meters per second squared. The time is 5.3 seconds. We're looking for delta x and delta y, and Vx and Vy. Delta x is just x without x0. It's x minus x naught, so it's delta x will be Vx naught times t plus 1/2 acceleration x times t squared. And if we plug in our numbers, that's 11 meters per second times 5.3 seconds plus 0. This all goes to 0 because there's a 0 in it for the acceleration. So that will be 58.3 meters. So it travels at 11 meters per second horizontally. 11 meters per second times 5.3 seconds gives us 58.3 meters horizontal. Vertically, we have our initial velocity in the y direction times time plus 1/2 our acceleration in the y direction times time squared. So that's 0 meters per second times 5.3 seconds plus 1/2 times 0.96 meters per second squared times 5.3 seconds squared, which gives us 13.5 meters.
So that's delta x and delta y. You know, if we want to find Vx and Vy, Vx is V naught x, Vx naught plus Ax t. So 11 meters per second plus 0 times 5.3 seconds. It's just 11 meters per second. It doesn't change. Vy is V naught y is Vy naught plus Ayt. So that's 0 plus 0.96 meters per second squared times 5.3 seconds, or 5.1 meters per second. That clear to everybody? Okay. This is another very similar problem. Do you want to do this, or do you want to just skip on to the next thing? This is worked out in the slides, so you can always look at the solution. But this is basically the same problem with slightly different numbers, and the acceleration is in the x direction instead of the y. I'm not seeing anyone who wants to do this, so I'm just going to skip through this. You can look at it in your own time. It's there because I was splitting the lectures right at that point, and so it was a refreshment. Well, let's talk about the basic equations for projectile motion. So for projectile motion, it's these equations with some assumptions. We're going to ignore air resistance. Acceleration due to gravity is g. It's 9.8 meters per second squared downwards. And we're going to ignore Earth's rotation. So if the y-axis points upwards, acceleration in the x direction is 0, and acceleration in the y direction is negative 9.8 meters per second squared. So in general, for projectile motion, acceleration in the x direction is 0. Acceleration in the y direction is negative 9.8 meters per second squared. This simplifies the equations. The acceleration is independent of the velocity. No matter what the velocity is, no matter what direction you're moving, the acceleration from gravity is g downwards. So here are the basic equations for projectile motion. For x, we just drop all the acceleration terms because acceleration in the x direction is 0. So x equals x naught plus v naught x times t. Vx is v naught x. Vx squared is v naught x squared. Y equals y naught plus v naught y times t minus 1/2 gt squared. Vy is v naught y minus gt, because acceleration in the y direction is minus g. And Vy squared equals v naught y squared minus 2g delta y. So if I go through these equations over here for projectile motion, I can erase this term, I can erase this term, I can erase this term, and I can plug in minus g everywhere I have acceleration in the y direction. So minus 1/2 gt squared minus gt minus 2g delta y. And g is 9.80 meters per second squared. The book sometimes uses 9.81. They're both within the range of actual acceleration on Earth. It varies a bit depending where you are. So these are the basic equations. And here is a guide to figuring out which equation to use. This uses equations with delta y instead of y and y naught, and delta x instead of x and x naught. because it's from a different book. But delta y is just x minus x naught. I mean, delta x is x minus x naught, delta y is y minus y. But here, you use this equation. If you're dealing with position, time, and velocity, use this equation if you're dealing with final velocity and initial velocity, and time. And you use this equation if you're dealing with velocities, final and initial velocity, and position, but not time. And then this is the equation you use for displacement in the x direction. For this chart, you can reference, it's in the slides. I thought it was helpful. So thinking about this, if a fish is dropped from the crow's nest at the top of the mast of a ship, when the ship is at rest, the fish will land in a bucket directly in front of the mast. If the ship was traveling at a constant velocity and ignoring air resistance, would the fish land in front of, behind, or in the bucket? So in the first case, ship is not moving. You drop a fish from the mast and falls straight into the bucket. If you repeat the experiment where the ship is moving, so the bucket is moving at some speed horizontally, and the fish initial velocity horizontally will be that same speed, will it land in front of, behind, or in the bucket? What do you think? Anybody? So behind the bucket, it's going to lag behind because the ship is moving. Okay. Anybody else? So if there is air resistance, behind the bucket would be correct. Because the drag from the air resistance will slow the fish down and it'll end up behind the bucket. But without air resistance, the bucket and the fish start with the same horizontal velocity. They will keep the same horizontal velocity the entire time. And the fish will land in the bucket because the horizontal velocity will just remain constant the entire time. So the bucket and the fish have the same horizontal velocity. And so the fish will land in the bucket. And I think I'm going to stop there for today. And we can get started with the lab. Are there any questions before I get started with the lab? Okay, I'm going to stop sharing. And